One asked me about how to do problem 1 of your homework. I just briefly go over it. Okay? So problem 1, h of t must be equal to e to the minus 3t u of t. Okay, so this thing is Fourier transform to something like 1 over 1 plus 3j or something like that?
3 plus 3j omega.
Omega, right? Okay, so this Fourier transform to that. So
3 plus j omega.
3 plus j omega.
Yeah.
Okay. So this Fourier transform to that, and then you're given that the input ft is sine of 2 pi t. And f of omega must be equal to 1 over 2j delta omega minus 2 pi minus delta omega plus 2 pi. Right, this thing Fourier transform to that. And then you multiply, and y of omega is f of omega times h of omega. Okay. But then you have this sampling property of the other function, so this just becomes h of 2 pi 1 over 2j delta omega minus 2 pi minus h of minus 2 pi 1 over 2j delta omega plus 2 pi, something like that. Okay, I might have a sign error somewhere. Then you take this back to the time domain, then this will be h of 2 pi 1 over 2j e to the j 2 pi t or something like that. And then minus 1 over 2j e to the minus j or 2 pi t. It can be recombined to be a sign. And then you write this in terms of a Fourier series coefficient e to the j and omega naught t, and it's to the minus infinity to infinity. You can compare these two series and then figure out what the coefficients are. Okay, and then figure out what omega naught is. Okay, you just compare and pick up the coefficients. You understand it? That you don't have to do a Fourier series expansion again, because this is a kind of Fourier series expansion. And then you can find f of 1, f of minus 1, I think there's only 2 terms, right? There's only 2 terms in the Fourier series. And then you can, omega naught is 2 pi, and then n is equal to plus or minus 1 in this Fourier series. Okay? I think that's all you have to do. I might have some sign errors on the blackboard, okay? So you have to watch out for my sign errors. So let's go to chapter 11 if you're done with this. Okay? Let's go to chapter 11. So here I'm using the shifting or the sampling property of delta function. Okay? I'm using the sampling property of the delta function delta omega minus omega naught times the function of omega is the same as delta omega minus omega naught f of omega naught. These two are the same. Okay, I'm using that to go from here to there. And then I can do Fourier inverse transform by a table lookup. And then I get something like that. Okay? Are there any questions?
Shouldn't the I transform be just ij instead of
What is that?
the multiplier for the for the sine transform? Shouldn't it be just ij instead of 1 over 2j? Yeah.
Sine is 1 over 2j e to the j 2 pi t minus e to the minus j 2 pi t, right?
Yeah.
So with Fourier transform this, I get a delta function, you get a 2j over here, right? I get a 2j over here as well. So that is the sign. Okay? So everything is quite straightforward if you know how to do table. Let's go to chapter 11. It's on Laplace transform. You can think of Laplace transform as a generalization of Fourier transform. And all of you have learned so much about Fourier transform. So you just learn how to generalize it. So this generalized Fourier transform. So a lot of things that you have learned about Fourier transforms, okay, still applies in Laplace transform. So what is Laplace transform? So let's do a simple experiment that you have a yt which is equal to the impulse response convolving with e to the st, and you have a linear time invariant and causal system. The input is just e to the st. Okay, and then the output, what is the output? Now, output is yt, which is ht convolved with e to the st. Okay? So let's look at this convolutional integral. Y of t is equal to h of t convolving with e to the st. And if I write this in detail, it will be h of tau e to the minus t minus tau with an s over here, sorry, with an s over here, the tau. Okay? The tau, and then I'm going to put a unit step function here, otherwise it may not work. Okay? So I'm going to put a unit step function over here, but not necessarily, I don't think textbook puts in a unit step function. Okay, because the impulse response is causal, this is linear time invariant causal system, ht equal to 0 for t less than 0. In order for this to represent a linear time invariant and causal system, because of that I need to only integrate from 0 to infinity over here. Then when I do this, then I will have e to the st. I break this into two factors, e to the st times e to the minus s tau. Okay? And then the integral I have left is 0 to infinity h tau e to the minus s tau d tau. Okay? So, this part over here, I can call it to be h hat of s. Okay, h hat of s, and then you can write this as e to the st h hat s. So, hence I can write the output y of t being equal to e to the st h hat of s. Okay, this is reminiscent of something that you have learned before. It's just a generalization of what you had learned before, that in the Fourier transform system, we always did this experiment that if you have e to the j omega t, out comes e to the j omega t times what? If the frequency response on the transfer function is equal to that. What is the output over there? This is times h of omega. Okay? Then for Laplace transform system, you have the same thing. You have e to the st, outcome e to the st h hat of omega s. So if I were to let s be equal to j omega, then the two systems are actually the same. Okay, so you can see that h hat j omega is h of omega in these two systems. Okay, so this is called the Laplace transform. H hat of s is the Laplace transform of h of t. So very much like a Fourier transform, it's just a generalization. Okay, it's just a generalization of the Fourier transform, and we have h hat of s been defined as 0 to infinity d tau e to the minus s tau h of tau. Or you can also write it in a t variable if you want to, dt e to the minus st h of t. So this is the generalization of Fourier transform. Okay? And you can also very easily prove that if y of t in general is equal to f of t convolving with h of t, that is what we found to be true for a linear time invariant system, is also linear time invariant and causal if the system is causal. So this statement is true for linear time invariant causal system. And if I substitute in the formula for Fourier transform, okay, if I substitute in the formula for Fourier transform and write the right hand side, assuming that it's causal, okay, let me see. If I take the Laplace transform of this, okay, if I take the Laplace transform of the right hand side, and then I get y of omega, and then I take the Laplace transform on the right hand side. Because it's a causal system, it must be 0. And if I take this e to the minus st dt, I would end up with the fact that this is just the Laplace transform of s multiplied by the Laplace transform of the impulse response. Okay, this can be proven quite easily. Let's go about and prove this. This, of course, has been proven for Fourier transform, and it is a straightforward generalization to show that this is also true for Laplace transform. So if we were to do this, then we can see that this thing over here, which is the right hand side, is equal to 0 to infinity dt e to the minus st, and then I can write this as a convolution h of tau f of t minus tau d tau 0 to infinity. Okay, and then I can exchange the order of integration and write this as h of tau, and then put the integration outside, put the d tau integration outside, and then put the dt integration inside, t minus tau e to the minus st. Okay, I've just exchanged the order of integration in the two integrals. Okay, and how do I perform the inner integral? How do I perform the inner integral? I can do a change of variable and call t minus tau to be t prime. Okay, dt is dt prime, and then the inner integral becomes something like dt prime f of t prime, and then what is to be replaced with t? T is equal to t prime plus something, right? Plus tau, very good. Okay, and then what do the range of integration go? Range of integration was previously from t is equal to 0, when t is equal to 0, t prime is equal to minus tau. To minus infinity, right? When t equal to plus infinity, t prime is plus infinity. So the integration goes as such. Okay? So we have this, and then we can actually take one of these pieces outside and write this as 0 to infinity h tau. Take one of these pieces outside, e to the minus t prime. I have to put in my s here. I forgot my s. Okay, that's very important. I need my s. E to the minus st prime, e to the minus s tau. I take that piece outside and put e to the minus s tau outside, and then leave the integral outside. Okay, what I'm left with the second integral is minus tau to infinity dt prime f of t prime e to the minus st prime. Okay. I claim that if this is a linear time invariant system, okay, if I want the output to only become non-zero when when t is larger than 0, if I require this of this output, I better have the output such that the input have to be such that f of t prime is equal to 0 for t less than 0. Because I have already made the output such that yt is equal to 0 for t less than 0. So for a linear time invariant causal system, okay, if this is LTIC, if the impulse response is something like this, okay, and this is my ft, and this is my ht, and this is my yt, I claim that my yt looks something like this. Is a causal signal. This is my yt. It need not necessarily be like that, but yt is causal, ht is causal, ft must also be causal. So I can change this to 0. Okay, I can change the lower limit of integration to 0, and hence this would be just a Fourier transform of f, or the Laplace transform of f. This is just the Laplace transform of h. Okay, so this statement is proved that this is s. Okay, this is s. The Laplace transform of y is equal to the Laplace transform of h times the Laplace transform of f. Okay, so this is in general a true statement for a linear time invariant causal system. This is y of f. So very much like what we have found in Fourier transforms as well. Okay. So there is something peculiar about Laplace transform for the ROC. ROC stands for region of convergence. Okay, what is the region of convergence for a Laplace transform? I can do that for example 11.1, for instance. Example 11.1 says that if my impulse response is something of this form, okay, this is a function that is exponentially growing. And its Fourier transform actually does not exist. Its Fourier transform does not exist, but we can find its Laplace transform. What is the Laplace transform? This is the definition of what Laplace transform is. So, the Laplace transform, in this case, will be defined to be 0 to infinity e to the t ut e to the minus st dt. Okay? And in order not to miss this little piece here, it's generally preferable to define the integral from 0 minus. Okay? Most textbooks will define the lower limit of integration to be from 0 minus, so as to make sure that you are unambiguously integrating from this point onward. Okay, actually it doesn't matter because the area that's underneath here is of 0 measure unless you have a delta function there. So most Laplace transforms are defined with 0 minus. It actually doesn't make a difference unless you have a delta function there. Otherwise, defining it from 0 or 0 minus are the same thing. Okay, let's look at the Laplace transform of this. Then, because this is being defined from 0 minus, and this is always 1 in the integrand, then I see that this is the same as integrating this with 1 minus s dt. Okay, combining these exponents, I have this one, and then if I integrate this, I get e to the t of 1 minus s divided by 1 minus s 0 to infinity. Okay, 0 to infinity. And s is equal to infinity. Okay, how do I evaluate this thing at t is equal to 0? Sorry, t is equal to 0 and t is equal to infinity. Okay, how do I make sure that this thing actually vanishes at the upper limit? So I better make sure that e to the t of 1 minus s goes to 0 when t goes to infinity. How can I make sure that this quantity goes to 0? I better make sure that s better has a real number that is larger than 1. If I make sure that real s is larger than 1, okay, s is a complex number. S can be sigma plus j omega. Okay, s is a complex number. If I make sure that the real part of s, or sigma, is larger than 1, then e to the t 1 minus s would be e to the t 1 minus sigma minus j omega, okay, is equal to e to the t, or minus j omega t, e to the minus sigma minus 1t. So if I make sure that sigma is larger than 1, or real part of s is larger than 1, when I evaluate this function in the upper limit when t goes to infinity, it vanishes. Okay, it vanishes. And then I'm left with the lower limit. Okay, so lower limit, this thing evaluates to 1, so I have the Laplace transform of this being minus 1 over s, or it can be written as 1 over s minus 1. Okay, so this is some peculiarity with Laplace transform. It always exists, but you have to define the values of s for it, for which it can exist. Okay, it always exists, but only for specified value of s. So if I define s to be a complex plane, okay, s is equal to sigma plus j omega, and the imaginary axis is equal to omega, okay, what it says is that this integration, this transform, would exist only for values where the real part of s is larger than 1. Okay, so which means that for s, this is a complex s plane, for s on this side of the plane. If I take my s values to be over the shaded region, then the integral converges. Then they say that the Laplace transform of this function exists. So it only exists for that part of the complex plane. Is this clear? So it's something in addition to Fourier transform. This Fourier transform would not have existed because this would not have converged if we were to perform a Fourier transform. But with Laplace transform, we have a choice of choosing what our S should be. We choose our S so that the upper limit can be evaluated. Even an exponentially growing function can have a Laplace transform, but you have to pick your S values to be here. Is this clear? Okay, so this is something new that you have to learn in Laplace transform. Okay, any questions? Okay, no questions, very good. Okay, let's, what is that? I take the real part out. I take the imaginary part out and put it over here. I evaluate this function, okay, for values of S, where S is given by a real part plus an imaginary part. Then it has this property that sigma must be larger than 1 in order for it to be exponentially decaying, so that this upper limit can be evaluated. If I define that to be the case, then I have to pick my S on this part of the complex plane in order for the Laplace transform to exist. Okay? Okay, let's do some of the examples in the textbook. If there are no questions, we can do more examples. So this is called a region of convergence. Okay, this is called the ROC. Okay, the region of convergence. So let's do example 11.2. Well, you have f of t been defined to be e to the minus 2t, u of t minus e to the minus t, u of t. So let me make sure that this is absolutely the same as what I have in the textbook. Okay? So how do I find the Laplace transform? F hat of s, which is the Laplace transform, will be given by usually 0 minus, okay, to infinity dt f of t e to the minus st. This is just a definition. Okay? So when I substitute that in, I get 0 minus to infinity dt. If I have the first term, then I have ut e to the minus 2t e to the minus st for the first term. And then the second term is just minus 0 minus infinity dt ut e to the minus t e to the minus st. Okay? The unit step function is always equal to 1 in this range of integration. Then I have to integrate this function e to the minus s minus 2t, okay, for the first one, and then I have to integrate e to the same thing, u goes to 1 always, s minus 1 t. Okay? So it is almost the same as this one over here. So you integrate, and then you get 1 over s minus 2. Okay? And then the upper limit of integration would only converge for the first term. Maybe I can put it back in. Okay? E to the minus s minus 2 t, 0, t equal to 0 to infinity. And the upper limit of integration will only vanish if the real part of s is what? If the real part of s is, that should be a plus, sorry. When I combine these two, I should get a plus. And combine these two, I should get a plus. I should get a plus. Okay, sorry about that. So the real part of S must be larger than minus 2, right? The real part of S must be larger than minus 2 in order for the upper limit to vanish. Okay? If I do the same thing over here, I would have S plus 1, oh sorry, this should be plus 2.
There's a negative sign also.
I have a negative sign.
Because it's equal to negative S plus 2.
Oh yeah, I should put this plus sign e to the S plus 1 t, and then evaluate at these two limits. Okay? So, the first one would converge and become 1 over S plus 2 if real part of S is larger than minus 2. Okay? The second one will converge to 1 over S plus 1, okay, if the real part of S is larger than minus 1. Okay? So two of them have two different regions of convergence. The ROC for both of these terms are different. So if I were to sketch it, I will put omega, I will put sigma over here. Then the first term has ROC that is, if this is minus 1, this is minus 2. Okay, the first term will have regions of convergence that looks like that. The second term will have region of convergence that looks like that. Okay? So, but I have to define the region of convergence to be common to both, so that both terms would converge. So the region of convergence for this Laplace transform is this one over here. This one with the crisscross. Okay? So the total ROC is defined to be real of S is larger than minus 1. That is the total ROC. Because it's in this region that both of the terms exist. If I define it to be that, then the second term would not exist. The first term exists, but not the second term. So the region of convergence has to be defined so that both of them can exist. So it has to be that crisscross region over there. Is this clear to everybody what the region of convergence is? So another thing to notice is that this location over here, okay, is called a pole. Because this is a location where this function goes to infinity, and this location is also called a pole. Okay? And the region of convergence is always to the right of the pole. In this case, to the right of the rightmost pole. Okay? And we also did have a pole for this one. Remember the Laplace transform for that was equal to that one over there. Okay, that is also a pole. The region of convergence is always to the right of the pole of the Laplace transform.
One question.
Yes?
Probably out of this class's topic, but if you have the pole sketch, you just evaluate the integrals using residue theorem.
Yes? What?
Can you just evaluate the integrals using residue theorem?
Not in the forward transform. You can always do that in the inverse transform. There's something called the inverse Laplace transform, which you will learn later. Okay? Which is, we're not covering over here at this point. We're just doing forward transform. And then there's something called the Cauchy's residue theorem in complex variables. Then you can invoke a theorem to perform a lot of these integrations in closed form. Okay, you can actually pick up the residues of the poles to do this inverse Laplace transform. Okay, we'll do that later. Okay. .3. What about if the impulse response is just a delta t? Okay. What is the Laplace transform? The Laplace transform in this case is defined to be, and this is important now that we define this as 0 minus, okay, delta t e to the minus st. Because if it's not 0 minus, it would not have picked up that impulse response or impulse function that is at the origin. And using the shifting property of the delta function, okay, this is just equal to, what is it equal to? What does that integral evaluate to? What should t be evaluated at? 0. So we get 1. Okay, we get 1. Okay, we get 1. So that is example 11.3. What is the regions of convergence? Since there's no pole, on the complex plane, the regions of convergence is everywhere. Okay, everywhere on the complex plane, there's a region of convergence. So S can be anything, and we will have this result. Yes?
So if we have instead of delta t, when we have it, if we have delta t minus t naught, we just integrate to
say if what happens is this is equal to that.
yeah.
Okay, then that would be just 0 to infinity, 0 minus, okay, delta t minus t naught e to the minus s t minus t naught. Oh, sorry, no.
Just t naught.
T. And then using the shifting property of this is s t naught. Okay, that is what it evaluates to. Okay.